Now there are actually two different ways we can go about doing this problem at this point. There's even some other methods too once we learn a few other rules. But for right now, there are at least two different ways. So the way that I'm seeing most people starting this one out is by trying to find that derivative of cosine squared, for instance. And when we're doing that, I'm seeing a lot of different things cropping up, a lot of errors actually cropping up as we do that. So instead, let's remind ourselves about what that means. So I got my -5. What's it mean to square something? Yeah, to multiply it by itself. So that means that cosine squared is actually cosine of x times cosine of x. And then the same thing can be done with the sine. So then we have sine x, sine x. That now allows us to use which rule? Yep, product rule. Because notice I have a product of cosine times cosine there. And I have a product of sine times sine there. So yes, we can use product rule there. So now if you're feeling a little bit stuck at that point, now you can progress from there. And so here's our first line of using product rule there, where within each of those we're doing original times derivative plus derivative times original. I went ahead and left the -5s outside, but you could have actually used them inside as well as part of the functions, and you still end up with the same answer at the end. I just do note, though, I had to kind of scoot this down to the next line, so we are subtracting this whole thing, remember. All right, and then it's just a matter of doing the cleanup from there. And so then we can go and we can combine, like here we have a negative sine cosine of x and another negative sine cosine of x. So if I put those together, I get -2 sine cosine of x is there. And we do the same thing with the other parenthesis as well, where I have a sine times cosine plus a sine times cosine, so that gives me 2 sine times cosines. And keep distributing from there. And so then when we go ahead and get rid of all of the parentheses, you can see we're looking at this now, where we have 10 sine cosine of x minus 10 sine cosine of x, which is the same thing minus itself, right? So the whole thing equals 0. All that to equal 0, which, now the part where maybe you kick yourself a little bit, kind of makes sense, because I did say there were two different methods to do this, right? The other method is that we could have started by just rewriting our original function up here slightly differently. Like I could have factored -5 out of both terms, right? And then just to make things a little bit more obvious, what if I wrote the sine first and then the cosine? Well, sine squared plus cosine squared equals 1. And so really this original function was actually just a big fancy way to write y equals -5. And the derivative of -5 is 0. You could have done it either way. That is a good reminder, though, that we always want to look for ways we can simplify these things at the start. Because by simplifying it, you can often make your life a whole lot easier, and then you don't have to go through all of this where we're more likely to make an error than we are if we just go through this, just because there's more steps and they're more complex. So if you can simplify it first, do so. Now go ahead and please find the derivative of this function. And again, for this one, there's multiple methods you could use. If you want to, you could go straight to finding your derivative at this point, which means using product rule within the quotient rule. Or you can try to simplify it first. I'm going to simplify it first. So for instance, the first thing we could do is we could actually cancel out those signs. But it can simplify even more past this, too. So if I write it all in terms of sine and cosine, secant is 1 over cosine on the top, tangent is sine over cosine on the bottom, and when you look at it this way, you can now see that those cosines will also cancel out. And so actually the whole thing is just y equals 1 over sine of x, or in other words, cosecant of x. All right, now I'm ready to find my derivative. What is the derivative of cosecant of x? That's all there is to it. And we know that derivative of cosecant of x because that's in our notes that we took down yesterday. All right, and so this definitely saved us a lot of work from having to use product rules and quotient rule and all that kind of stuff. Of course, as a little side note, math teacher, detail-y kind of stuff, this is of course true only where it's actually differentiable. There are some asymptotes, some things like that in this kind of a graph where we'd be dividing by 0. So just remember that these things work as long as we are not at one of those points where it causes us to be dividing by 0 somewhere along the line. Now, I know you missed words, so we got to throw a few words in there. Take a minute here, read through this, and then start actually working this one through to be able to figure out what the answer would be. All right, so start working this one through. We need to first find velocity. So velocity, remember, is the same thing as s prime, the derivative of the position function. So I'm going to go ahead and just find the derivative of 4 cosine of t. So then the 4 is still going to be there because the constant still hangs out. The derivative of cosine is a negative sign, so then that makes it negative 4 sine of t. There's our v of t equation. A of t, remember we find by doing the derivative of velocity. Or, if you want to think of it this way, you could also think of it as the second derivative of position. So basically, I'm just going to go up to this function. I'm going to take the derivative of that. So the derivative of that would be a negative 4 times the derivative of sine is cosine, so it's negative 4 cosine of t. All right, those are our two general functions. The last step that we have to do here is we need to know specifically what's the velocity and acceleration of this object after 2 seconds. So I need to figure out what does v of t equal, and what does, not v of t, v of 2, and a of 2. So we're going to go ahead and be finding out what both of those values are. So for v of 2, we're going to do negative 4 times sine of 2, which is going to be negative 4 times about 9.09, don't round in the middle, multiply that by the negative 4, and when you do that, we end up with a big long decimal. I'm going to go ahead and just round it 2 decimals as an arbitrary choice. There's nothing magical about that particular one, so that's going to be 3.64. What are our units on this answer? Oh yes, negative, thank you, forgot to write that in there. What would our units be here? Well, we started with s of t, right? What's the units on s of t? Our position? Yep, that's the centimeters up here. So if that's measured in centimeters, when I do the derivative, remember it's the derivative with respect to time. So that would be centimeters over the time. And the time here is measured in seconds. So that would be centimeters per second for this. So centimeters per second for our units there. All right, now we repeat the process for a of 2, where we're going to be doing negative 4 times cosine of 2 this time. And so that means we're going to be doing the negative 4 times about negative 0.416. Then we multiply that by the 4. And that gives us an answer of about 1.66. And again, we need our units, right? Well, looking here at our acceleration function, we know that we did the derivative of acceleration. So that means we start with centimeters per second. And then this is going to be all over whatever t is measured in, again, because we took the derivative with respect to t. And t again was measured in seconds. So really you're looking at centimeters per second per second. Well, we've seen this before. We've seen there's a shorter way to write this. Instead of centimeters per second, which is correct, we can write that a little bit shorter by writing it as centimeters per second squared. And then that one's done. So in this one we had to take multiple derivatives, right? Well, multiple derivatives is another thing that we've been talking about here and there along the way. So let's practice finding multiple derivatives here. Please find the 27th derivative of this function. So if I just started taking derivatives of this, because I got to go out to 27 here. The first derivative, of course, is negative sine. Then the derivative of negative sine is negative cosine. Then the derivative of the negative cosine would be a positive sine. Then the derivative of sine is cosine. But notice then, it starts repeating itself, right? Because after I've done 4 derivatives, I'm back to where I started from. So every 4 derivatives, I'm going to end up with the same cosine of x. So heading into 27, what's the last derivative where we got a cosine? So which derivative, again, gives us another cosine of x?
24.
Yep, that's the 24th, because that's the next multiple of 4 that comes along. So we know the 24th is cosine. So then that would mean that this would be the 25th derivative. This would be the 26th derivative. And so the 27th derivative then would be this. And so the derivative then is just sine of x. The 27th derivative, actually, I should say, is sine of x. And so we can use these kind of patterns, right? Because with sine and cosine, they start repeating themselves. Okay, so with that idea in mind, what would the 100th derivative be of 3 sine of x? All right, so as we take a look at working this one through, we again start by thinking about what would the derivative be each time and where does it start cycling through itself again. And just like the last one, it's every 4 derivatives, it's going to get back to where it started from. So you see there, the 4th derivative gives me 3 sine of x again. All right, so knowing that then, I'm going to go out to 100. Well, the nice thing about 100 here is that 100 is a multiple of 4. So then I know that's where it's actually starting to repeat itself. So it's back to the 3 sine of x at 100. So there's nothing else that we would need to do on that one. So our answer is 3 sine of x. We're just going to do 2 more straight derivative problems. So go ahead and write down and find this derivative now. Right, and so as you go and find this derivative, yes, you are going to need to use quotient rule here. So there's not a lot of nice, pretty simplification we can do here. So we just really need to just start with quotient rule. So that's going to be low d high, so that's going to be secant of x times the derivative of our top function. So the derivative of tangent, you might have needed to check your notes on that, and that's okay, is secant squared of x, but continue practicing it so you can get them down and memorized, because here pretty soon we will have a test on it and there will be no notes for that part. All right, and then the derivative of 1, of course, is 0, so it's just the secant squared of x there. Then minus high, so the top function exactly as it is, and then d low, so the derivative of the bottom function. So now the derivative of secant is secant tangent. All right, and then that's all over the square of what's below. And so that's going to all be over secant squared of x. And technically this is the derivative. But let's go ahead and actually get rid of all those parentheses, see if there's anything we can combine or simplify. Maybe there is, maybe there isn't. We really need to actually just do that work in order to be able to find that out. So secant times secant squared, that would actually be secant cubed. And so I'm going to go ahead and squish it all together like that. And then it's going to be minus And then we got to do a little distribution there. And so I'm not going to deal with this minus out front yet. I'm just going to multiply the tan by the secant tan, and then the 1 by the secant tan. And then I'll worry about putting the minus in. Otherwise, I might forget about flipping a sign somewhere along the line. So this is going to be secant of x, tangent squared of x, minus secant of x, tangent of x. All right, and then, of course, that's all over secant squared. Now, normally, I would then do the next step on the next line, but so you don't have to sit there watching me write for a long time, I'm now going to go ahead and put that negative in, which means that that first term becomes a minus, and then the next term becomes a plus. That'd be the only difference in the next line of work there. All over secant squared of x. All right, so now that we got rid of all the parentheses, is there anything we can simplify here? Yeah, it looks like there is a little bit of simplification we can do. Because on the top, well, I don't see any like terms on the top that I can add or subtract, because they all have secants in them, but they're not all times the same thing. You know, like these two have tangent in them, but one's a tangent squared, the other one's a tangent, so we can't just add them. But we do have secants and everything in the top, and there's secants in the bottom. And so I can cancel out a secant out of every single term. So if we just do that part, then we end up with secant squared of x now, instead of secant cubed, minus tangent squared of x, because we got rid of the secant out of that term, and then plus, get rid of the secant out of this term, so that just leaves tangent. And then that's all over, again, take a secant out, that leaves us just with secant of x on the bottom. Any more simplification we can do? Nothing we're going to worry about now. There might be some obscure identity that we might be able to try to manipulate with here, but I'm not worrying about most of those. The main identity that you'll find yourself using of the trig identities is the sine squared plus cosine squared. A few others might come up here or there, but that's really the only one that you have to have memorized for day in, day out, even on the tests kind of usage. This will be the last derivative that we practice with today then. So please write down this problem and again, find the derivative. Now, the very first thing that I would recommend doing in this particular case is doing the sine plus cosine squared. Now, the big thing to remember though is that sine plus cosine squared is not the same as sine squared plus cosine squared. Remember, you'd have to multiply sine plus cosine times sine plus cosine, and when we do that, we do get this middle term. But we now need to find our derivative, but you notice that we can simplify it a little bit more, right? Because you'll notice that within our parentheses, I have sine squared plus cosine squared right there. And so that part of it right there is going to give me a 1. So it's going to be pi times 1 plus 2 sine of x, cosine of x. And now it's going to be much easier to find that derivative. So work from there. You can either distribute the pi in now, or you can do it later. All right, so here's my work where I do actually use the product rule on that function. And so from there, it's just a matter of doing a little bit of cleanup. So we're going to turn this into y prime equals, let's say that's going to be 2 pi. Cosine times cosine, of course, is cosine squared. So that's going to be cosine squared of x. And then this last term, I do see a negative there. And so my plus is going to become a minus. And that's going to be 2 pi sine squared. All right, so now we're looking to simplify it, right? I guess one thing we could do is we could pull out that 2 pi, right? Now, do we have to factor the 2 pi out? No, but it might make it easier for us to see something else. So let's go ahead and do that. So we have cosine squared rather minus sine squared. What does cosine squared minus sine squared equal? Cosine squared minus sine squared. That's it. It doesn't become anything fancy. That's not one of our identities. So this is it. And either of these two forms here is fine. You didn't have to factor out the 2 pi. You also could have. Either way is fine though. But that's our final answer.